And if it was a negative number, suppose you have negative 12, then what you would do, you will put 1 here, okay, and then take the 1100 there as it is, okay. And that means keep the rightmost zeros and 1 as it is, don't change them, and then flip the rest. By flipping rest means this will convert to 0, that converts to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. That is your negative 12 stored there. The other method that we learned was negative 12 plus 32,768. That will be 32,756. So binary representation of this number, that will be from here to here, whatever you have. So 2's complement, the one I did here, I flipped the numbers. That's called 2's complement. That's a shorter and easier method than adding 32,768 and doing the binary. This is what we did in the previous lecture. Okay. So more formally, the first day, okay, if the number is positive, you put first digit would be 0 and 15 bits of binary representation of that. If the number is negative, integer is negative, the remaining 15 bits are the binary representation of whatever that integer you have plus 32,768. That's the first method that we learned. The other method that we learned was using 2's complement. By 2's complement, you ignore addition of 32,768. Whatever number you have, ignore the negative and find its binary. Then you store them, but then don't change the first, all the trailing zeros on the right hand side and the first one, and all of the digits, just split them. And that would be your representation. So what it says, to find the 2's complement, write the positive number as a 15-bit binary, retain all zeros at the right end and the rightmost one, and reverse all other bits. So that would be your. So let's look at some example. Find the 16-bit computer representation of the integer 11,459. So this is 11459. In binary, it is 10110011000011. How many digits are these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. These are 14 digits. However, I have 16 bits there, where the first bit is for the sign bit. Since this number is positive, first box would be 0. And then I have to add another 0 to make the rest as 15 bits. Yeah. Now think for a moment. Think for a moment. If this number was negative, how you can, and you have the binary representation for the positive, how you will convert that? Okay. The method that I told you, first bit is the sign bit. You will have 1. From this binary, retain rightmost zeros, there is none, and rightmost 1. So I would retain this 1 then, that's it. All other numbers, I'm going to reverse them. So this one becomes 0, then 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1. So this is the binary representation of negative 11,459. This is how negative 11,459 is stored on 16 bits computer. You agree with me? if I assess you on these questions now, right now, would you be able to do that? So that means you don't understand. Still. If you say, no, I'm not ready, that means you don't understand the method yet. There is only very few rules we have done, and you should be able to solve the puzzle by using these rules. So this is just some examples. If I keep doing them, you keep nodding your head, you will say, yeah, good, we understand that. But you won't understand until you do it yourself. So these were the examples. We did that in the previous lecture. I should not be repeating them again and again. I've done a few. So we move on to our next topic. But firstly, just think, if we can store on 2 bytes, right? Then how it works on 32 bits or 64 bits. On 32 bits, method is exactly similar. So instead of having 2 big boxes, for 32 bits you would have 4 big boxes. Okay? And if you are looking for 32, the storage goes the same way. So these would be like that. Okay? And each one split into 8 parts. 8 parts. 8 parts. I don't know. Just to say. So that makes 32 bits. Okay, as we see in a computer that has 2 bytes available for storing integers. So the range is from this to that. If you are working on 32 bits, the range would be negative 231, 2 to the power 31, 2 to the power 31 minus 1. And if it's 64 bits, you would have the range between minus 9 quintillion to plus 9 quintillion. Quite big, in other words. Any questions? And the process is exactly the same as we did for 16. Now, arithmetic with integers. Are we going to add, subtract, multiply, divide? So we'll now look at how computers actually add and subtract. Okay. So, I tell you what, if I say addition is the same as subtraction, would you agree with me?
Plus negative 1.
Yes. Exactly. Addition is the same as subtraction. Think of that if I asked you to do 2 minus 3, oh, let's say 5 minus 3, and you said, no, I won't do that, I will do 5 plus minus 3. Essentially the same. So if I say 5 minus 3, you can say, no, I don't want to deal with this. I want to deal like 5 plus and then another number. It's absolutely correct. This is a negative number, right, that you can feed in a computer. And that is a positive number that you feed in a computer, and out goes the number 2. Right. So, by doing this way, what advantage you are getting?
You're using the integers you have in the bytes.
We're using integers which are?
Like you're using integers which have representations in the bytes.
Of course, we have to write them in bytes. Yeah, in this. Okay, fine. But the same would go here, right? The advantage of writing this way or that way.
You don't have to subtract. Just so you don't have to subtract.
Yes. We don't have to introduce another operation in the circuitry. Computer would only have to deal with one operation. It wouldn't have to deal with 2 operations, plus and subtraction at the same time. Okay, do you understand that? So in the circuitry, computer will only be dealing with one operation. That's a big advantage. When you know that there is, you can use the key. Suppose there are two keys reserved for operations. Now you are allowed, you can have only one key, and the other key you can disperse off for other purposes. That's a huge boost. Okay. At some stage in this subject, later stage, when we do cryptography, a brief section in cryptography, we'll learn how advantageous it is if we already know first few digits. You might not understand at this stage, but at that stage you would. How many of you watched imitation games? What did you get from Enigma? Why Alan Turing managed to crack the code? They kept on working for some long time. Couldn't crack it. But then in a pub, he eavesdropped on something, and pop goes the idea. What was the idea?
They always sound how they always say how to let them leave their message.
Okay, yes. What advantage from there you would get?
You know what they're going to say. If you decrypt those words, you use it to decrypt the whole thing.
No, you're right there. Yeah. But let me rephrase it. Same way. There are, say, that many long characters your computer can code. You know, your processor is strong enough to deal with just this many bits. However, the message they are receiving somehow is sort of longer than that. Okay? Your machine efficiency can work up to a certain limit, and after that it just fails. Keep on running and not giving you an answer. Why? Because the digits in the code are far too many than the machine capable of. If you know that there are always this many fixed digits or fixed information, then you can ignore them. When you ignore that information, the rest of them the machine is capable of coding or decoding. That's how we managed to do that. That if you have the handicap of this many words already, the rest of the code can easily be cracked by the machine. So that's the advantage he had. He just figured at that time. Now, with arithmetic for integers, we don't have to deal with negative. We don't have to introduce a new operation. Positive can handle the subtraction as well. Addition can handle the subtraction as well by writing in this form. It's not here yet, but okay. First of all, let me come to that in a minute. Instead of doing 16 bits, it would be slightly long. We restrict ourselves to just 4 bits. Why? Mechanism is exactly the same. It's for ease of calculations for us. Instead of dealing with 32,768, we just deal with 8. Okay. We look at very, very small operations. We don't look at the big numbers, just for the ease of calculations. So we confine ourselves for 4 bits only, where the first bit is the sign bit, and then the 3 bits for the integers. If we only have 3 bits, the range would be from -8 to +7. Okay, and yeah, it works, and the calculations would be extremely simple. If an integer n is stored in 4 bits, the process is the same as I said. For positive, we would have 0 bit, and for negative, we will have 1. So if the integer is positive, the remaining 3 bits are binary representations of n, including zeros. For example, if you have 6, it will be stored as 110 and 0 here to indicate that the number was positive. If it was negative 6, it would be 1010. You can see I retained rightmost zeros and ones and flip that, and this one indicates that it's a negative number. Do you agree with me? Right? Exactly the same method, but we are only doing it for 4 bits. So you can also use 2's complement, which I just did, if you like. Let's look at the example. No, don't look at the example, I've already done that. 4-bit representation of 6, it will be 0110, and 4-bit representation of negative 6 would be 1010. Now, this is the 4-bit representation of negative 6. What is this number actually?
Plus 86.
This number actually, if you think of that, what would be? This would be, I think this is 10, actual 10, yeah? Okay, so you obtain this number. If you think of this representation would be the same as negative 6 plus 16, which is the representation of 10. So it's 16 translation invariant. It's just a trick. But anyway, the fundamental method stays the same. Now, 4-bit representation of negative 5 would be 1 for the negative sign. Okay, and then you would have the other representation. What that would be, negative 5 representation would be, you think of, ignore the negative, and the binary of 5 would be 101. You retain rightmost 1 or zeros, so that would be just 1, and then flip these two, you would have 1 0, and that is your first bit is the sign bit, and then 0 1 1 bit. Any questions? Now, let's make a table of 4-bit representations. Okay, I would write down on the iPad just to actually for recording purposes. Otherwise, I would prefer to write on board. Now, what are the number in range? In 4 bits, how many different integers we can store? Yeah. You can store sort of different integers, 16 different integers you can store from negative 8, as we have done before, 2 to power minus 2 to power 3 to 2 to power 3 minus 1. So this is minus 8 to 7, and these numbers are, if I want to store them, negative 8, negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, and then you have 0, 1, 2, 3, 4, 5, 6, and 7. Right? Let's write down their binary representation, should we? Okay. So let me start to write down 0 in 4 bits can be written as 0, 0, 0, 0. You agree with that? Yeah. Okay. 1 would be 0, 0, 0, 1. 2 would be 0, 0, 1, 0. 3 would be 0, 0, 1, 1. 4 would be 0, 1, 0, 0. 5 would be 0, 1, 0, 1. 0, 1, 1, 0. And 0, 1, 1, 1. Yeah? Now let's write down for the negative numbers. Should we? First digit would always be 1 because it's a negative number. Now we have to find remaining 3 digits. For negative 8, it would be Do you agree with that? How many of you agree with my answer? Raise your hand. One. How many of you agree with that? Soon it will just, I think, disappear. How many of you agree with my answer? 2, 3, 4, 5. Anyone else? Actually, most of you are correct. I'm wrong. You didn't agree with me. Actually, internet just disconnected. That's all right. We were not doing super, things that we can't do without that. No. Wow. Thanks, Zoom. All right. We have -8, -7, -6, -5, -4, -3, -2, -1. 0, 1, 2, 3, 4, 5, 6, 7. This is extremely easy. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. That's 0, 0, 0. Right? And here, the first digit is 1 because it's a negative number. The remaining 3 digits we have to find.
Just write the right side list in reverse from the last 3 digits.
In reverse.
Yeah, so you start from what 0 is at ending 1, so it'd be 0, 0, 0. Just using those last 3 digits. So you get to the top, so negative 8 is 1, 1, 1, 1. Is that right?
Yeah, negative 8 is 1, 1, 1, 1. Let's write it down. 1, 1, 1. That's what you're saying.
-1, 1, 1, 1. Based on the 2's complement.
Yeah. So, look, negative 8, let me explain that again. Please try to understand what it is. I'll give you the shorthand. I actually explained a very quick method as well. That was just add 16 in it, and whatever you have, that would be your representation. Okay? But for the time being, let's say if you've forgotten that, just remember 2's complement. 2's complement is, forget the negative, and write down binary representation for 8. And what is that? 1, 0, 0, 0. Yeah? Okay? Now, it says retain all of these, rightmost all of them, and 1 as it is. Okay? And then we do the complement. Okay? So, but this is already there, so we can't apply it. So this is going to be So if you were doing 16 bits, what you do, so you would have, it can't be this, 16, so you would have 0, 0, 0.
Yeah, so it's exactly the same as the first list. Then it's just 1 instead of 0.
Yeah, yeah, it stays the
So
same.
it's the same cost.
Yeah, because, if I am dealing with this 7, so you would retain that, and it would become 1, 0, 0, and you would work that to get 1. Yeah, that's right. And for negative 16, sorry, negative 6, you add 16 in it, and that would become 10, which would be 1010. Okay. And then you would have, now you can see the pattern, do you? You have 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 for negative 5. How did you get that? You see, you retain 1, and then you flip this. This becomes 1 and 0, and you have 1 here anyway. For negative 4, you would have 1, 0, 0. For negative 3, you would have, what you would have? 1, 0, 1. For negative 2, you would have 1, 1, 0. And for negative 1, you would have all of that. Okay. So you can see here, look, 1, 1, 0, 1, 1. So firstly, what you did, you go in you have 1 here, and then 2, 3. Now after that, this is fully exhausted. Then what you do, you put 1 here, and bring these 2 zeros down. Then 1 is there, then this is down. 1 is there, then this 1 0 is there, and then 1 1. And this is in the reverse order. So you put 1 in here, and then these triple ones. 1 there, 1 1 0. 1 there, and then this value. That. Did you agree with that? Okay. So I'm going to connect with this. Look, no technology is perfect. Now, but we are doing our best to provide best resources. Okay. In this case, so it connects on internet by Wi-Fi. If I want to live stream, then of course sometime internet drops. What can you do? Okay. So the trick that I explained was, if you want to find 4-bit representation of these numbers, don't worry about negative number. This is exactly the same. If I want to find 4-bit representation of negative 8, I will find negative 8 plus 16, which is 8, which is 1, 0, 0, the first one. Okay. Negative 7 plus 16 is 9, which is 1, 0, 0, 1. If you know the binary representation of positive numbers, negative numbers are extremely easy. You can extract them from the positive numbers. Where are you? So since it's not connecting, there is some kind of error. What I'm thinking to do is to use my alternate resources. Anyway, this is not that biggie. No, this is not the one. Oh, come on. Thank you. Come on. Okay, here we are, week 2, lecture 5. So where were we? We were storing integers, and we learned up to 64 bits. Then what we are doing now, we are doing arithmetic with integers. When we say arithmetic, that means just addition, subtraction, multiplication, division. And representation of an integer, first we look at how you represent them in 4 bits. Exactly same method as you learned for 16 bits, but bit concentrated. We developed this table over there, as well as I did that previously. Okay. All right, and from there, now you know how this representation takes place. And now what table shows? Table shows that for integers between 0 and 7, the computer representation integer is the same as 4-bit binary. And for negative numbers, it is just number plus 16, right? Same. So the example, the computer's representation of -3 is 1101. Look at here, which is what? Which is the computer representation of number 13. So it's simply -3 plus 16. Okay. All right. So then we move on to addition. Now, we know we did in the previous lecture how to add binary, multiply binary, and subtract and all that. What possibly could go wrong? Okay, firstly, just let me know, do you know how to add in binary? Okay. If you don't know, that of course you have no practice. You have not looked at that, so it's not a tablet that I give you, you eat and you got everything. So the only way you can do it is by doing questions, no other method. Okay, so suppose you know how to add, and now you're a 4-bit computer. So the question here is, if I'm adding 3 plus 2, what answer should I get? Absolutely. So that means if I'm adding 0011 plus 0010, I should get 0101, right? And I do get that in this case. Do you agree with that? Right? So if you add these two numbers, 0 plus 1 is 1, 1 plus 1 is 10, you get 0, and then 0 plus 0 is 0 plus 1 is 1. So you get that representation. What could possibly go wrong here?
Calculation error?
Oh yeah, that always happens. Other than that,
Put them in the wrong places. In the wrong.
no. I think these are just de facto graphical errors, which casual errors that happen. So, what could potentially computer give you an error that says you punch into numbers and it gives you error? You would notice that in calculators, right?
Give you a negative number.
What?
Give you a negative. So it's close.
So if you add two positive numbers and answer gives you negative, well done. That's a very good answer. Okay, think of some examples. If I'm adding 4 plus 6, yeah? What is 4? 4 is 0, 1, 0, 0 plus 0, 1, 1, 0. What answer I'm getting? I would get 0, 1, 1, 0, 1, 0, 1, right?
Yeah, and that's also negative 6.
Which is negative 6.
That's also like 10 if you were to do it from 0
Right.
to.
10 is not allowed in 4 bits. So when when you add these two numbers on a 4-bit computer, you will get error. Because this number is not allowed.
That's a
Sum of
negative.
two positive numbers is not, cannot be negative.
A computer doesn't recognize a negative number.
It does. It does. But sum of two positive numbers cannot be negative. That problem is called overflow problem. Similarly, by adding two negative numbers, if you're getting a positive number, that's where you get an error. Any questions? Okay, so let's look at this in more detail. Now look at adding two numbers on a 4-bit computer. Sometimes this can't be done. For example, the result 4 plus 6 is too large to be represented. Okay, 4 plus 6 is 10. It can't do that. But if it does, it can't. Your answer can't be negative. However, provided we look only at numbers that can be added. That can be added means whose result stays in the range. Okay? If the result stays in the range, then yes, it's a right method. Now, why you get errors on calculators? When you do bigger and bigger and bigger and bigger multiplication, once you cross the permissible level, it gives you error because it cannot calculate beyond 32 digits or, let's say 20 digits. It can't calculate beyond 20 digits. Right? I don't know the exact number it calculates to, but it has a limit. When the multiplication goes across that limit, beyond that limit, it gives you an error because it's not saying that, it's wrong. It is saying that it's not in my range. Okay? And that's where humans come into play. They manually play with the machines then. So, however, provided we look only at numbers that can be added, addition is carried out in the usual way using the representation of numbers, except that a 1 in the 5th column from the right is ignored. If you get 5th column 1, if you add two numbers and you get a number in the 5th column, you simply ignore that. Okay. Example, let's look at negative 2 plus 6. Okay. Negative 2 representation, let me move it down slightly. So what is negative 2? Negative 2 is 111 0 plus 6 is 0 1 1 0. You add them up, you get 0 0 1 0 1. So this is the 5th column entry when you sum them up. And if it is 1 there in the 5th column, you ignore it. So automatically your answer is these 4 bits which are allowed. So it will return you an answer of 4. Okay. This is how it goes there, right? So can you do this example for me? Verify that 4-bit computer correctly carries out the addition, negative 1 plus negative 5. Remember, as I said, we are not having negative in the circuitry as an operation. Negative numbers allowed. As an operation, negative is not allowed. There. Okay, can we do this question then? Do you get -6 as an answer? Good. If you got -6 as an answer, yeah, that's the right one. So if I'm doing -1, no, sorry, what I'm doing, -1 plus -5, so yeah, -5. So my answer should be -6. Let's look at -1. It is 1, 1, 1, 1, and plus -5 is 1, 0, 1, 1. So I add them up. What I got, 1 plus 1 is 0, 1 there, 1, 1 there, 0, 1 there, 1, and then I got that. I'm going to ignore it because it is 1 in the 5th column. So my answer is 1, 0, 1, 0, which is for -6. Yeah. So this is correctly, we got the correct answer for that. Any questions? Okay. So what are some comments? Verbally, I have already stated them. Our 4-bit computer cannot possibly produce the correct answer to 6 plus 7 because the answer is 13. It's not in the range. Okay. So 13 is too large a number for the computer to handle. Because we are only allowed 4 bits, and 4 bits you're only allowed between -8 and 7. Provided we consider only numbers that can be added, that is numbers whose answer stays between -8 and 7, it gives you the correct answer. If you have 16 bits or 32 bits or 64 bits, process is exactly the same. If you are in 16 bits, if you're adding two numbers whose sum is more than 32,768, you will require an addition digit in the 17th column. If it is 0, then of course you can't do that there. Alright, if the answer is more than that, then of course it will give you an error. And in 64 bits, if you're adding two numbers and if the sum is more than 9 quintillion, right? Just like on your calculators, when you're multiplying big and big numbers, the range exceeds their permissible value, then it shows you an error. Okay? This problem is called overflow problem there. So, yeah, on the math stays the same. If you would have 128 bits computer, then still it is confined to certain bits. Right? You would have 2 to the power 128 between 127 and 120 2 to the power 127 minus 1. That value. If it exceeds that, then of course you cannot add them. Do you agree with me? Okay. So there are, whatever bit of computer range that you take, there will always be possibility of going beyond. Right? So up to certain digits you can do, and after that you can't do that. These are our restrictions there, nothing more than that. So far what we did, we started off this subject with a binary representation of integers. Okay? Then we looked at how those binaries can be converted into octal and hexadecimal. So there are different bases. Then we looked at arithmetics of different bases. Arithmetics means addition, subtraction, multiplication, and all that. So firstly, what we learned? We learned how to convert numbers, integers or reals or rationals, integer or rationals into binary. Then we learned how to convert these numbers into octal or hexadecimal, because those are the shorthand representation of binary. Just as a shorthand. Actual representation in computer are always in terms of binary, but as shorthand, easy conversion, we look at the bigger bases. And then what we worked on? We worked on how computers would add, subtract, and multiply numbers. Now then we looked at, okay, actually what happens, how computers store integers. We have not looked at decimals yet. Did you notice? We only look at integers like 12 or 6. We have not looked at how computer would store 6.27. That's the next topic that we're going to do. So far what we looked at, how computers store integers. We looked at it depends on the processor speed. If it's 16 bits, or 32 bits, or 64 bits, then what are the ways or how many integers it can store? All right? We started off with 16 bits, and we said, okay, you can store at most 65,000 and certain numbers, up to that many different integers. So that means it's from negative 32,768 to positive 32,768. Right? That many integers you can store on 16 bits. Then we thought, okay, this is how we know how computers store integers on 16 bits. Then how they manipulate, how they add, subtract integers within computers. We said, all right, we can do this, but instead of doing on 16 bits, that would be a bit bigger value. We confine ourselves 4 bits only, so that the questions that we're dealing are with on a lower scale, smaller values, easy to deal with. And then we learned how these would add, and we said that, okay, in 4 bits, if the sum is in permittable values, it will always give you the right answer. However, if the sum is not within the range, it will show an error, and that's because of that overflow problem. Okay, this is your, so far, the 5 minutes that I took is your 5 lectures. Okay, we're going to meet again at 2 o'clock in the room 205 upstairs to do the tutorial, or the workshop you call it. Right, so let's see, I'll see you there then. There was a bug.
How you going with reading, mate? Well, these clocks. Too bad. Just trying to. Yeah, I know. So that's like